Okay. So James's question is, what is your email ID? Because the one support gave me was unresponsive. Okay, let me just take a look. Let me just take a look. How did we miss the question? All right, all right. After the session, let me take a look at the support and see how did we miss the question. Okay, all right. So great, great. So far what we have learned is the back propagation, and we were basically going through the various activation functions there. And let me just see. Okay, okay, all right. So yes, let me just go back and give you a bit of context. So far what we have done is we have learned backpropagation. We have trained our deep neural network, one using TF-learn library, where we had to do nothing, and at the same time we designed our own deep neural network using TensorFlow. That opens doors for us to create more architectures, more that opens up for the more experimentation. And and basically the art in case of the deep learning is to be able to come up with some architecture that solves your problem, right? Right now we have only one architecture. We have only discussed one form of architecture, and we have also discussed some of the variations in it. And right, so but there could be many more combinations, as we'll see as you go ahead, like say for example convolutional neural network, the CNN. It has a slightly different layout from what we have learned in this. Okay. Oh, all right. So let me go back again where we were. All right. So basically, we have learned how to design deep neural network using TensorFlow and how to run it. And we were learning how to fine tune your neural network. Okay. So a question from Binta is, when will be the text available for the topics? All right. All right. That also need to be addressed. Um, Then a question from James also, what is expected conclusion date for this course? So we are planning at least, other than this week, we're planning at least 4 more days, okay, meaning 2 more weeks other than this week. All right. So that's basically not a, we we want to complete in that time, but we would not be rushing in order to complete. But that's kind of an expected date. 2 more weeks after this week. All right. And a question from Pavan: are you sharing? Okay. All right. So yes, I was not sharing the screen. And okay. Okay. Question from Minta is, why does the topic 10, dimensionality reduction machine learning, need to enroll? Okay. Let me also take a look at this part. Okay, let me take a look at this part. All right. Okay, so there are few questions that need to be looked at. Okay, let me just make a separate note of it before I forget. Okay, I'm just making notes of this one. All right. All right. So there is a question from Gigi. La Last day, how do we decide iteration to be 40? Okay. How do we decide? Okay, let me come back to that one again. Yes, yes. Okay. So yeah, that's what we are going to discuss. So here basically the introduction to neural networks. This right? All right. So basically, question is why number of why the so first question would be that why batch size of 50. Quick answer is that if we increase batch size, it's going to load more data into the memory, and therefore it would consume more RAM. Therefore, keeping a batch size moderate is a good idea, neither too big, not too small. Number of epochs is basically a kind of a hunch that after after 40 it will saturate. After 40 it will saturate, but general strategy is to the general strategy called early stopping, whereby we stop the moment the accuracy is kind of either saturates or starts instead of increasing, it starts decreasing. So it's kind of a hunch that it is 40 iteration, but we can try increasing because here there is still a scope of increasing. If you see, no, actually here it is has the cross validation accuracy has kind of become saturated. Do you see that? So here it was 9808, then 988, and then it started decreasing. So it's generally the way we work is that we try to do the early stopping, and specifically the moment we observe that the cross validation accuracy is has started going up consecutively multiple times, that point of time we just stop. Okay, instead of decreasing, it starts decreasing instead of increasing. Then we realize that okay, the valid accuracy has started going down, and that means that it's time to stop. Okay, a question is the graph did not display for me, so need to have a condition inside to. Yes, that's right. We need to have condition inside the accuracy. Yeah. All right. So this is where we basically track. All right. So you could try with more numbers and see if you could get better accuracy. All right. Wonderful. Wonderful. Great. Great. So we were able to train our own neural network, and we were starting to discuss the fine-tuning neural networks. Now, in case of neural network, what we have understood is that we could have either multiple layers or or less. So either we could vary the number of layers, or we could vary the number of neurons in every layer. Number of neurons in every layer. So so when we are doing hyperparameter tuning, we have these two parameters to choose, and we can actually increase both. We can increase the number of neurons as well as increase the number of layers. So as a general thumb rule, increasing number of layers gives you better results as compared to increasing the number of neurons per layer. Okay. So here you can see that the above one, this one is, yeah. The third thing that we could vary is, the third thing we could vary is the activation function on each layer. The fourth thing that varies is the weight initialization logic. So next next uh, next discussions are around these: changing number of neurons, changing number of layers, and changing the activation function for each layer, and as well as the weight initialization logic. That's what we are going to discuss. So weight initialization logic again is a very important aspect, and a lot of work is done in the weight initialization, because weight initialization is something that leads to great results, along with increasing number of layers and number of neurons and the activation functions. All right. So you can see that the above one is using a sigmoid function, because sigmoid function is little curvy, and the below one is using a step function like ReLU. Now, how do we know what combination of hyperparameter is best for our task? In simple answer, in simple answer, we basically combine the random search and grid search together. Okay. So what does it mean? What we do is basically we try all permutations of our hypothesis that these are the things, if we change, you'll get better results. So we kind of combine all the hyperparameters, and first we do the random search. Once we have the approximate values of various layers and various hyperparameters, then we fine tune from there using the grid search. In random search, we only pick few permutations of hyperparameters and try few random permutations. And in case of the grid search, what we do is we fine tune by trying all permutations. Okay, so we start with random search, we understand in what range should our various hyperparameters be, and then do the grid search. All right, so one solution is to do the grid search with cross validation to find the right parameters. Cross validation means we so how, I hope that all of you are comfortable with the term cross validation. I'm sure Bintao, Gigi, Pavan, Pratik, Ross are comfortable. James and Balaji. I think Balaji is also comfortable with cross-validation. All right. Yes, great, wonderful. So all of you are comfortable with the term cross-validation. It essentially means that we break down the data into multiple folds and test on one of the fold and train on remaining folds, right? So since there are many hyperparameters to tune, and since training a neural network on large dataset takes a lot of time, we will be able to explore a tiny part of hyperparameter space in a reasonable amount of time. So therefore, it is much better to use random search as compared to the grid search in the beginning. And then we can fine tune it later using the grid search. All right. So, okay. Yeah, that's what it says. So let's start with number of layers, number of hidden layers. Number of hidden layers basically decide whether our network is deep or shallow. Okay, shallow means lower number of hidden layers. Deep means more number of hidden layers. And we generally call deep neural network to the networks where we have more than one hidden layer. So for many problems, we can just begin with a single hidden layer and we would get better results, reasonable results. So an MLP with just one hidden layer can model a lot of complex functions provided it has enough neurons, right? For a long time, people believed that this, the researchers were convinced that there was no need to investigate any deeper neural networks. There was no need to investigate any deeper neural networks because of because increasing number of neurons was giving them good enough accuracy. The MLP with one hidden layer was giving them good accuracy, and computation power wasn't available that much. So for a long time, the researchers were kind of comfortable with not investigating deeper neural networks. Now, the they basically overlook the fact that deep neural network have much better parameter efficiency than shallow ones. What does it mean? It means that increasing number of layers will give better results as compared to increasing the number of neurons. Okay, so this means that they can model complex functions using exponentially fewer neurons than shallow nets, and that basically makes these faster to train and so on, right? So the general strategy is that we can begin with a single hidden layer and get results and can model even complex functions provided it has um, enough neurons, and then we start with adding more layers. All right. So in basically we start with the shallow and then move on to the deep neural network. Deep neural network have much higher parameter efficiency than shallow ones, and right. So to understand why deep neural network has much higher parameter efficiency than shallow ones, consider the following analogy. It's a very important part that to understand why it is that deeper layers give us better performance than as compared to the number of neurons, right? So let's say we have a shallow network which has one layer. Now you have a choice. You have a choice that should we insert one more hidden layer? Should we insert one more hidden layer, or should we just double the number of neurons in the existing layer. Imagine that we have this. Now, question is, if we insert an equivalent hidden layer here, will that give us better results? Or if we insert same number of neurons in this same layer, so will increasing neurons gives you better performance and better output, better accuracy, or adding one more layer would give you better results? So the general answer is adding one more layer gives you far better accuracy at lower cost. If you increase number of neurons, the computation increases drastically. But if you increase number of layers, the computation does not increase drastically. It basically increases only slightly as compared to the increasing number of neurons. So a good analogy is that suppose we have to draw tree individually, branch per branch and leaf per leaf, right? So let's say we had to draw a huge tree. If we do not utilize what we learned earlier, what if we do not utilize what we learned earlier, then our efficiency is going to be really bad. But if we reutilize what we learned or what we drew earlier, then we can just copy paste the previous one and then create the tree easily. The same is true with the deep neural networks. So this is an analogy here. Let's say on the input layer, let's say we have learned something here, right? At this layer, the same learning is being used. Okay, just like copy pasting the leaves. So what and the other way to look at it is this, that at this point if we insert one more layer, if you're inserting one more layer, what's happening is, let's say here we are inserting, let's say here we are inserting one more layer. Okay, so to compute the values of that, to compute the values of the weights here on this layer, what would it require? Just we need to multiply the derivatives of the previous one in order to compute this. Because the training the good part about training the network using backpropagation is that we reutilize what we learned earlier. Correct? So even in the backpropagation, when we are adjusting the weights, we basically reutilize what we learned earlier. We reutilize what we did earlier. So basically, when we are adding one more layer, we will be reutilizing the previous set of computation, and therefore adding a layer will cost you less with respect to GPU or with respect to CPU or with respect to computation as compared to increasing neurons. All right. So that's how you can think about the increasing of number of layers. All right. In the retrospection today, as we see that there are deep neural networks and they work fine, it is easier to argue that deep neural network was a great idea. But a couple of years back, maybe like 5-6 years back, deep neural network was not such a good idea, right? So, but today, as it seems to work, we can take analogy and we can understand and settle down with the fact that the more number of hidden layers give us better results than adding more neurons. All right. So, though it is actually theoretically impossible to argue that there's no theoretical proof as such. There's no theoretical proof as such to prove that deep neural network will give you better results than the shallow ones. All right. We can just base it on analogies. We can just base it on our experimentation and the evidences as the proof, but no theoretical proof. All right. So so this is an example of the analogy with respect to real life, and the other point that could help you understand is that the real world's data is often structured in hierarchical way, just like a tree, or just like the way we have multiple layers, the next layer operating on the learnings from the previous layer. That's what is happening. So in real world, most of the structures are hierarchical, as we will see more examples. And let's understand this point by the way of faces, recognizing the faces. Say, let's say we have a model in which recognizes faces. So you can think of it as if that the lower hidden layers, meaning the beginning layers, model the low level structures like line segments and the various shapes and orientations, and the intermediate hidden layers combine these low level structures to model intermediate level structures like circles, squares, ellipses, and so on. And the higher hidden layers, as we go from left to right, the output layer combines these intermediate layers to model high level structures, example faces. Okay, so basically, basically the basically this is what I'm talking about. So in if let's say data is coming from this side, the shallow networks, what they do is they would try to convert the input data into lines and structures, because we are combining the values from multiple ones. And then the second layer representations would make curves out of it and so on. And then third layer representation would try to understand the faces. Okay, this is how generally we perceive the, this is how we perceive we understand this, understand deep neural network in this way. Okay, so it doesn't happen exactly this way, but this is how we can understand that. Okay, the first layer is for rudimentary understanding the lines and the curves and very basic shapes, and the second layer or the hidden layer is a little bit more complex. It understands the little bit more complex parts, and then the third layer basically does more work. Okay, and we will use the concept of transfer learning as we go ahead. Okay, we have whole session on transfer learning. So the hierarchical architecture helps DNN, deep neural network, converge faster to a good solution. It also improves their ability to generalize to new data set. All right. Now, question is, how does hierarchical structure, hierarchical as in layer over layer, help DNNs generalize to new data set? Right? We trained it on some data set. How will it generalize to the other data sets? So we'll try to answer it using another example. Imagine that as imagine that suppose we have already trained a model to recognize faces in pictures. Okay, let's say we already have perfected our neural network with the faces in pictures, and now we want to train a new neural network to recognize the hairstyles. All right, we want to go one step further. All right, we want to go one step further. Or let's say we have trained a neural network to recognize faces, and from the faces we want to go one step further, saying let's recognize now the expression on faces. Right, when we do that, first we have to recognize the faces, only then we'll be recognizing the extra features like hairstyles, or we will be like emotions. That will be kind of the next logical layer. So that's how we generally uh, look at the deep neural network. So we can kickstart the training. We can kickstart the training by reusing the lower layers of the first network. The previously, let's say we have a well-trained neural network which recognizes faces. That these are the faces in the photos, and then instead of randomly initialize, let's say you are given the neural network which is working perfectly fine on the faces, and now you want to reutilize it. You want to reutilize it instead of starting from the beginning. You want to utilize an existing trained neural network which recognizes faces for recognizing the hairstyle. So you can just start with the weights and biases of the first few layers of the neural network that recognizes just the faces, and you can initialize them to a value, and then add a new layers to it, add new neural networks, and then initialize the new only to the new layers, so not the previous layers. So all we are saying is that when we say that we are taking the learning from one project to another, all we do is we take the weights and biases of various neurons to the new one and add more layers on the deeper side, on the right hand side, to recognize, to do add on the previous one. That's what it means by transfer learning. This is also called transfer learning. All right. So this way the network will not have to learn from the scratch. All the lower level structures are that occur in most pictures would be there. So it only has to learn the high level structures like hairstyles and expressions. All right. So for many problems, we can just start with one or two hidden layers and it will work fine. And we can easily reach, like for example, we easily reached 97% accuracy on MNIST using just one hidden layer and few hundred neurons, and above 98% accuracy with two hidden layers and the same total amount of neurons, with in roughly the same amount of training time. All right. Though using a deeper neural networks, the accuracy as of now, which people have achieved, is around 99.7%. All right. If you take a look at Kaggle, there are a couple of solutions which basically have reached 99.7 in case of MNIST. So you can see that with just a couple of layers, we were able to reach a very decent accuracy of 97 plus. And if you want to go beyond that, you want to go further, then we might have to add more layers and further more strategies. All right. So for more complex problems, we can gradually increase the number of hidden layers until we start overfitting the training set. For more complex problems, we can gradually increase the number of hidden layers, and we can start overfitting the training set until we can start. So the moment we start overfitting means it is memorizing, and hence the cross-validation accuracy will start dropping. And at that point of time, we stop. And also what we learned is as a conclusion that the very complex tasks such as large image classification or speech recognition typically requires networks of dozens of layers or even hundreds of layers, and they need a huge amount of training data. Now, let's see how we can decide the number of neurons per hidden layer. The number of neurons in input layer is determined on the type of input. So if we have basically number of neurons in the input layer is a function of how many features do we have, right? In case of image, when we are feeding image, the number of features was 784. So the number of neurons in the input layer was 784. The number of output layer is determined by what kind of output we have. Is it multi-class classification? Is it binary classification, and so on? So number of neurons in the output layer basically is decided by the problem statement. So input and output both are controlled by the problem statement. It is only the hidden layer that hidden layers that we have the control over, increasing or decreasing number of neurons. So for example, in case of MNIST, we had 784 input neurons and 10 output neurons. And as for hidden layers, a common practice was, not is, a common practice was to size them in the form of a funnel, right? In one of the examples, we have used 300 and then 100 neurons in 2 layers. Similarly, here, the general strategy was to start with the same number as neurons as the input layer, and then gradually decrease them like a funnel to reach the output. But in today's time, this is no longer a practice. We generally go with equal size equal size equal size layers, equal size hidden layers in the network. All right. So we basically had an example where the first layer was having 300 neurons and the second was having 100. So in our case, it was 784, 300, 100, and then 10, right? So that looked like a funnel. However, this practice is not common now, and you may simply use the same size of hidden layer. For example, all the hidden layers with 150 neurons, that's just one hyperparameter to tune instead of one per layer. Right. So if we have equal number of neurons in all the layers, then also we'll get decent output. And the advantage of that one is that while we are experimenting with hyperparameters, we just have to change the number of neurons in equally on all the neurons. So there will be only one parameter instead of one per layer. Okay, that's a bit of advantage. Now, just like for the number of layers, we can try increasing the number of neurons until it starts overfitting. So whether we increase the number of layers or increase the number of neurons, in both the cases, it would start overfitting after a point of time. What is overfitting? Overfitting means it starts memorizing. It performs really good on the same test, on the same data set on which it was trained, but it does not perform good at all at the data which it has not seen so far, right? That is the overfitting. Overfitting means memorizing entire thing what it has already seen, and performing great on the same data which it has been trained on, but does not perform good at the data it has not seen so far. So in general, we will get better payoff by increasing the number of layers than the number of neurons per layer. Unfortunately, as you can see, finding the perfect number of neurons is still somewhat black art. So, so, so the conclusion is that use cross validation, try all kind of neurons, and and uh, and try the grid search to see how it is performing. All right. So a simpler approach is to pick a model. Simple approach is to pick a model with more layers and neurons than you actually need. Then you use early stopping to prevent it from overfitting. Okay. Early stopping as in we observe that if our validation accuracy is dropping, that means we are overfitting, and then we basically stop there. And sometimes this is also called as stretch pants approach. Instead of wasting time looking for pants that fit perfectly, that match your size, we use large stretch pants that will shrink down to the right size. All right. So instead of trying to guess the perfect number of neurons, so what we do is we start with really more layers and more neurons, and then uh, try to see if we are going to stop early. Okay, and if we need to stop early. So that's how that's the general approach is. All right. Now, in most cases, you can use the ReLU activation function in the hidden layers or one of its variants. It is a bit. Now, so far we have talked about only the number of neurons and number of hidden layers. Okay. So the next part is the next thing that we could change is the activation functions. In most cases, using ReLU function is perfectly okay in the hidden layer. So what is activation function? Output of after we combine the inputs by multiplying the weights and summing all of the values, we pass that output through a function called activation function. And whatever is the result is given to the next layer, right? So in most cases, we use the ReLU activation function. And again, what's the use of ReLU? What is the use of activation function? Activation function Activation function brings non-linearity into your network. Otherwise, it is like linear regressions in multiple layers. And adding an activation function brings non-linearity to your neural network. Okay, so that is the purpose of an activation function. All right, so in most cases, you can use the ReLU. It is a bit faster to compute because there's nothing much to compute. In case of ReLU, we just return 0 in case x is negative. Otherwise, we return x as such. So there's nothing much to compute, and therefore ReLU is good enough. And also the gradient descent, because while we do the back propagation, we are going to use, it is basically going to do the gradient descent. It does not get stuck on the plateaus. We'll talk about this part in a bit more details. That uh, plateaus as in the gradient descent does not drop to 0. Okay, when we talk about vanishing gradients, this will become far more clearer. And so it is due to the fact that it does not saturate on large input value. It does not become constant on, it does not become 0 on large input values. So unlike the logistic function or hyperbolic tangent function, both both of the logistic function as well as tan h, the hyperbolic tangent function, both of those actually give value within between my between -1 and 1. In case of logistic function, it gives max value up to say 1. Therefore, both of those kind of saturate, and hence the gradient would kind of become constant or 0, and hence it won't move further. We'll talk about this part a little bit more when we talk about gradient descent, right? So, so for the hidden layer, ReLU does good enough, and for output layer, the softmax activation function is kind of good for classification tasks. Okay, because that's what we do. And basically softmax activation function, what it does is it converts the decimal number into probabilities by dividing by sum of all, by dividing individual by sum of all, kind of normalization. And then that's what softmax does. Now, for regression tasks, you can simply use no activation function at all in the output layer. You don't need to use an activation function. If we are using the neural network for the regression tasks. Now, so that was a quick overview of fine tuning. So we will actually talk about more activation functions in the next session. All right. So let me continue because the next session is kind of continuing from exactly where we have. All right. So In this session, we are going to take a look at more activation functions. We will learn something called batch initialization, batch normalization, and then we will learn something called transfer learning as part of this session. So this is the next session on the deep neural networks, and this is a quite important session, and it is going to be definitely interesting for all of you. All right. So we actually built, so far we have, we were introduced to the artificial neural networks, then we trained our first deep neural network. It was a shallow neural network with only two hidden layers, one with 300, other with 100. The shallow neural network will not work if we have to deal with complex problems such as face recognition, voice recognition, and so on, right? So in that case, in case we want to do really complex recognition, we may need to train a deeper neural network containing many layers, each containing hundreds of neurons and connected by hundreds of thousands of connections. So now, if you have to do the face recognition, like face recognition, voice recognition, or anything, what do you think the challenges would be? Okay, let me give you the slide for the next session. All right. Also do the git pull. All right. Okay. Okay, so here's a question for all. Question is, what will be the challenges in training such deep neural network? Anybody? Yes? Yes, one is time. Good. CPU cycles. Okay. Good. Good. All right. Great. Um, is everybody agreeing with Pratik that there will be time and memory? Is there anything else, do you think, that could be an issue, could be a challenge when we are training the deep neural network? It'll be complex, okay. And yes, it'll start overfitting. Good, good, very good. Ross, Pratik, Pavan, James. Okay. Building an appropriate data set to train and test on. Yes. Okay. Because we would require a large amount of data, right? So Pratik's point was time, memory. It would be Pinta's point was complex, and then it could start overfitting, building an appropriate data set, right? And Ross's point is that black boxes are hard to figure out. Yes, and yes, we are making a guess on the black box. Okay, and all right, all right. So these are very good answers. So there is when we have millions of parameters, we have overfitting. Thank you, Pratik, for that answer. And it takes a lot of time. Yes. So And we also require a lot of data in most of the problems, right? So all of you have given a very good answer, almost everything covered. So we may face something called vanishing gradient problem. When since the deep neural network become complex, there are these problems that arise. And vanishing gradient problem was one of the problems that needed to be solved. And and you will see that why this problem called vanishing gradient arises when we have multiple layers. Okay, so let's take a look. Let's take a look. So let's take a look at the here in this chapter. We will go through vanishing gradient problem, explore solutions. We will also learn batch initialization or batch normalization, and we will also look at popular regularization techniques for large neural networks. All right. Now, one of the things that arises because of complex neural network is this vanishing gradient problem. What we do is basically uh, so in case of backpropagation, what we do is we go from the layer on the right hand side to till the input layer, right? And we keep on propagating the gradient from the right to the left. Gradient as in how is the error changing with respect to weight. We keep on computing that gradient, that derivative or differential of dE by dW at every stage by multiplying with the previous dE by the previous rate of change of error with respect to the previous value. Okay, that's what we keep on doing, right? That's what we did when we did manually. So all we do is from the right hand side till the input layer, we keep on going and we keep on propagating the error gradient. So once the algorithm computes the gradient of the cost function with regards to each parameter in the network, then it uses these gradients to update each parameter. Okay, so let's take a look. So once we have computed the gradient of this cost function here, and then we basically use, let's say, dE by d, the rate of change of error with respect to these outputs. Then rate of change of these outputs with respect to the rate of change of the values before the activation function, and then we basically keep on back computing the rate of change of each value with respect to another, and using the chain rule we compute that how changing this particular weight would impact the error, how changing this particular weight impacts the error. All right. So those who are not clear about backpropagation, please message me personally. I can plan out something, a separate session. I could take you back through the backpropagation steps, because if you are appearing or trying to solve a problem, you will notice that at the heart of all of the ideas is the backpropagation, and it's good thing that we took that seriously, as we are seeing more and more. As I was reviewing some of the interview questions here and there when you are going for interview, and it is better to understand the maths instead of not understanding it. Okay, so that's why if you are not clear about backpropagation, I would love to explain from the beginning and can schedule a separate session. All right. So let me know in case there is doubt, because everywhere you will see today as well, those concepts will matter. Okay. Now, so with regards to each parameter in the network, then we use these gradients to update each parameter, right? We change the weights with respect to the rate of, we subtract the rate by eta multiplied by the rate of change of error with respect to that particular weight. Okay, so if changing the weight is increasing the error, that means we decrease the weight. If changing the weight, if changing the weight is decreasing the error, we keep on in, sorry, let me put the everything again from the beginning. If let's say there is a weight here, if increasing this weight is going to increase the error, that means we decrease the weight. If decreasing this weight increases this error, if sorry, if increasing this weight decreases this error, then we decrease the weight. So whether to increase the weight or decrease the weight is a function of how error is changing with respect to this weight. Okay, and now how much, that again depends on how much is this error changing. If this error is changing, the rate of change of this error with respect to this weight is humongous, we change the weight in a large fashion. In case, in case changing this weight, the rate of change of this error with respect to weight is really tiny, then we don't change the weight. That means, that means changing this weight will not impact error. All right. So that's the general idea about the backpropagation. And so, so what happens is, since we are multiplying gradients, what happens is the gradients start to become really, really small, or really small, so that there won't be any change further in the weights. Okay. And after a while, when, since we are multiplying here, so you will see that we will be multiplying these gradients, and therefore the gradients, after being multiplied by 3-4 times, they will become almost like zero. The rate of change of error with respect to every weight will be zero, and therefore none of the weights will actually change. This is known as vanishing gradient problem. Now uh, let's take a example to understand it. Remember the sigmoid function, right? Do you remember the sigmoid function? We also call it logistic function, right? In which whatever value you put here, the sigmoid of x is e to the power minus x added with 1, and then the whole thing is inversed. Okay, so if alpha is really huge, this value is going to be tiny, and the value is going to be approximately 1. If alpha is really small, as in it is negative infinity, then this value is going to be really high, and therefore the overall value will become 0. So the value of this varies from 0 to infinity. 0 to 1, not infinity. The value, even if the value of alpha is changing from minus infinity to positive infinity, the value of sigmoid will be within 0 and 1. All right? So this is clear, right? Now you could draw it. You could actually draw the same thing. This is how it is shown. So, okay, before we move further, have you checked out the new code? All you have to do is git pull. Let me also repull it. Okay. Something is wrong. Okay. It is here. All right. So we could say, in this, we could say git pull. Okay. It says that, all right. Let me just check what's the difference. So it's only the outputs which are different. This is just the output that is different. There's not much of a change on my side. All right, let me just check out. Git checkout. Was there any change that I did? Oh, I'll just take a copy of this one. Git status. All right, so this one is modified. I'll just take a copy of this one and then compare later. Okay. All right. Okay, so we're going to say git pull and git checkout. Now git pull. Checkout basically overrides your local changes. All right. So I've just pulled training deep neural networks, and now we can just click on this particular file, or you can just refresh it. Okay. So you go to say here inside ML, inside deep learning, and there you will find training deep neural networks. Okay, so this is my file. Yeah, here, this is the one. All right, so right, so here, let me start from the beginning. These are the same utility functions required again here. So we are defining our own logistic function. This is how it looks like: 1 divided by 1 plus np.exp minus z. And then we are basically generating the linear space from -5 to 5, and 200 parts we are doing it. And then we are first plotting the lines. These are the lines that we are plotting, these lines. And then we are plotting plotting z. This is the linear space against the values returned by logit. Okay, and so on. So okay, so this is how it is, and this is how the logistic function looks like. Okay, so this was just to, you know, give you an idea. Now, when we do the differential or the gradient, or you can derivative, we get this kind of a function. Okay, so we get this kind of a function. Sigmoid of alpha 1 by 1 plus e, that's the actual one. If we do ds by d alpha, we will get this, right? So if you remember that the differential, we'll basically apply the chain rule. 1 by x is 1 by x square minus 1 by x square into then the bottom, the derivative of x. Here that will be minus of e to the power alpha e to the power minus alpha. That means the answer will be e to the power minus alpha, e to the power minus alpha divided by 1 plus e to the power minus alpha the whole square, right? When you write it further, the derivative looks like this. Okay, the derivative looks like this, which is equivalent of s into 1 minus s, right? S into 1 minus s. Now, question to all of you is, what is the maximum value of this? Sigmoid can go from 0 to 1, right? So the question to all of you is that what can be the maximum value of this s into 1 minus s? Anybody? What can be the maximum value of derivative of sigmoid? So when we differentiate sigmoid function with respect to alpha, or with respect to anything, with respect to whatever parameter it is, what would be the maximum value of this? So imagine that s is 1, so the answer is 0. If s is 0, the answer is again 0, right? So basically, if s is 1, for, well, the both the extreme, this derivative is 0, okay? If you look at the sigmoid function again, what it means is the rate of change at this point is flat, meaning it's not changing. The rate of change is not there, right? The rate of change on both extremes is 0, and the rate of change in this here somewhere will be highest. That's what it means by the max value of the derivative. All right. So how do we find out how do we minimize or maximize something? That's right. So how do we minimize? So imagine that we want to find out the max value of some expression. Okay. So what we do is we differentiate and equate it to 0, meaning we find the point on the curve where the rate of change is 0. That point could be minima or maxima. Okay. And then we can calculate. All right. Further, we can just plot the derivative, and this is how it looks like, right? At below minus 5, it is 0, right? The rate of change and so on. So you can see clearly that the derivative is maximum at the s equals to 0, right? And s equals to somewhere in between, okay? Somewhere in between. Now, what is that in between? Okay, so as we can see in the plot of the derivative sigmoid function, the output of the derivative of the sigmoid function is always in between 0 and 0.25, 0.25, right? And hence the value, actually here it is going, this is supposed to be 0.5. Okay, this is supposed to be 0.5, not 0. Okay, so this value is always between, oh right, the s is maximum, okay, yeah, correct. So at 0, what will happen is, at 0, what will happen is, at 0, alpha is 0, then it'll be 1 by 2, correct? Then s is 1 by 2. 1 by 2 into 1 by 2 is 1 by 4. That is the maximum value of derivative. So it's very clear that, so if we have an activation function as sigmoid, then the maximum value of the derivative is going to be 0.5, no matter what is our input. So sigmoid converted the infinite input, like really huge values, into something between 0 and 1, right? And further, the derivative of that value is going to be maximum 0.5. Okay. So if we have a univariate neural network which has only one input and there is one neuron. Okay, we have just one neuron. That's what we call univariate, and it has just say to two hidden layers and one input and output layer. So the activation function here is just a sigmoid activation function. So J returns the aggregate error of the model, right? So if you think of it, the rate of change of W1 with the rate of change of error with respect to W1 is going to be a multiplication of rate of change of error with respect to output here, rate of multiplied with rate of change of output with respect to the output of hidden layer, then multiplied with rate of change of hidden layer 2, the output of hidden layer 2, with respect to the output of hidden layer 1, and the output of hidden layer 2, and multiplied with this value. Is everybody clear about this expression? Yes? No? Okay. So the rate of change of this variable with respect to this is multiplication of these, right? So if you take a closer look at it, that this one is a multiple of so many variables, right? At any point, let's say the output at the hidden layer level, the rate of change of this one is rate of change of sigmoid multiplied with the W3, right? If you remember the formula where we had applied the expression. So if you see at any point the rate of change of output is a function of input in this following manner. Okay, so now you can see that, and here the rate of change of output of hidden layer 2 is a multiplication of rate of change of sigmoid function with respect to the output of hidden layer 2 multiplied with W3, because here there'll be a logistic thing applied. We'll be having W3 into X plus constant, right? Something of that on that line. So as in the kernel and the biases, or weights and the biases. And what are these weights? Again, the weights are initialized using one of the normal distribution and hen or standard deviation, the normal distribution or min max. In either case, we convert the data, we convert the input weights, or we generate the input weights somewhere between -1 and 1 or 0 and 1. Okay, if we are doing normal distribution, all our weights initially would be somewhere between -1 and 1, right? When we do normal distribution, you must have seen while we were initializing our weights, their weights, the values were somewhere between -1 and 1, somewhere between -1 and 1. Therefore, this value, the weights value is somewhere between -1 and 1, or you can say that lesser than 1. And this one is lesser than 1 by 4, right? If this is 1 by 3, this is 1 by 4, then the overall output is going to be 1 by 12. So you can see that individual value is going to be really, really small. So if we think of the same way, if the rate of change of this one is 1 by 12 and this one is 1 by 12, then it'll be 1 by 144. That's really, really tiny. That's really, really tiny. And essentially, we basically will keep on multiplying these numbers, which are really small, between 0 and 1, and the end outcome is going to be almost 0. So you can see that in back propagation, as we move backwards and compute the gradients just become smaller and smaller in every layer. And it becomes tiny in the early layers. The inputs, the input layer, the hidden layers, which are closer to the input layers, the gradients there become really small, closer to 0. And this is called the vanishing gradient problem. Okay, this is why the again you can take a look at the two layer neural network. So this is how you can visualize that here there was largest gradient, the rate of change of error with respect to um, outcome will be highest at this point, then smaller. So the gradients would keep on becoming, will keep on disappearing. So we have tried to show you that with respect to color, the darker one means the rate of change is higher. Here it's smaller. Okay, so the input layer is farthest from the output layer. Its derivative will be the longer expression using chain rule, hence will contain more derivatives whose value is less than 1, and hence will have the lowest weights, and therefore will be slowest to train. Now, why is vanishing gradient a problem? Anybody? I hope you all got it by now. Okay. Point from Ross is your neural network is not well balanced. Okay. Pratik's point is that it decreases number of layers. Kind of, yes. Basically, okay, let me see other people's answer. Anybody else? So why do you think vanishing gradient is such a big problem? Yes, Bintao, Balaji, Gigi, James, Pavan, Pratik, Ross. Reaching an ideal stopping point becomes difficult, okay? Yes, thank you, James. As it becomes minute, the weights can't change anymore. That's right. So initial layers kind of become defunct. Okay. So since gradient is really becoming small, and you remember that the formula where the weight equals weight uh, in previous value of weight minus, basically we change the weight in proportion to the gradient, right? We decrease the weight in proportion to the increase in the gradient, right? So if gradient is so we okay, let me put it again. I made a mistake. So we decrease the weight with the same value as gradient multiplied by some constant called eta or learning rate. So if that part which we are subtracting will become 0, then weights will remain as such, and hence the weight will remain as such, and no training will happen. Okay, so the first layers will become the defunct, and no training will happen. Right, right. Great, great. So you can think of it like in gradient when the gradient gets stuck at the plateau, right? And it doesn't converge anymore. It will become really slow. Okay, really slow. And if the gradients are hard, as in bigger, it drops really fast. Otherwise, it'll drop really slowly. Okay. So it'll converge to a local minimum. It basically kind of will stop and will converge at anywhere. It'll converge at local minima, not a global minima. Okay. All right. Now, So this is called the vanishing gradient problem. The second problem was, since the later layers are dependent on the early layers, if the early layers are not accurate, then the later layers or the lower layers uh, just built on inaccuracy. So if the first layer is not performing well, for the next layer, the input is basically the previous layer, right? Second layer will become the input layer for the rest of them. If those are not performing well, those are not giving correct input, then rest of it becomes corrupted. So early layers are responsible for detecting simple patterns and are building blocks for the neural network. Hence, it becomes important that early layers are very accurate, because those layers, early layers, are feeding data to the next one. A slight change in the early layers would impact the rest of the chain instead of only that one. Okay. Therefore, the early layers are important, and early layers are being impacted badly by vanishing gradients. Okay. So you can think of this way, that if this image was changed to something like this by the input layer, that this is how it will be perceived by the rest of the neural network. Okay. The other problem when we have a lot of layers, other problem is the opposite of vanishing gradient problem. Opposite of vanishing gradient problem is exploding gradient problem, right? So if our gradient's value is greater than one, then multiplying greater than one would keep on becoming bigger and bigger. Because of this, some layers may get insanely large weights, and the algorithm diverges instead of converging, right? Let me just take a bit of, right? So, okay, just if you go back here, if let's say we are here and the rate of change is really huge, so the next value could reach here, and again the rate of change is really huge, and therefore it'll reach here, and then rate of change is huge, so it'll reach here. So it'll keep on bouncing if the gradients are higher. Okay, so it'll never converge, instead it'll diverge. All right. So because of this, the algorithm diverges instead of converging. All right. So as we have seen that the deep neural network would suffer from the more number of layers, the more it chance. So if you have more number of layers, more multipliers, and hence the chance of vanishing gradients as well as exploding gradients become higher and higher. So, so different layers may learn at widely different speeds. Okay. Because of vanishing gradient problem, deep neural network were abandoned for a long time. We realized that, okay, this may not be suitable, and all right. Okay, so training the early layers correctly was the basis of network, but it proved too difficult that time because of available activation function and the hardware. Okay, good. A question from Pavan is, it creates dy by dx tends to 0. That's right. So overall weight would become 0. So weight will not change. Okay, overall weight will not change if dy by dx is 0, right? So if you remember our gradient descent was like this. So W equals previous value of W. This is previous value of W minus some constant called eta multiplied by error with respect to W, right? So if this is 0, this will remain like previous value and the rate of change will be 0. If this is huge, this is really huge, what will happen is this will suddenly swing to the other side, and then making it again huge, and it'll keep on swinging back and forth. Remember that this is if you see dw is kind of dE by something like, let's say, x and multiplied by W3, right? This is the formula that we just saw where we were multiplying. So if you see, if the weights are huge, what will happen? This rate is going to be huge. And again, if this rate is really huge, then the weights will become really huge, and then that cycle will continue. Okay. So that's basically the exploding gradients. Okay, so I hope this is very clear to all of you. Okay, all right. So Pawan, I was able to answer your previous question, but this next question, but learning rate will not control that. Okay, and okay. Yes, so learning rate definitely controls it. Learning rate definitely controls it. We can bring it down by bring down learning rate to a smaller size. But if gradient is really huge, then if that really huge number is multiplied with learning rate, it might still be really huge, which could swing it back, swing the back the value of W to other extreme, and hence that change will continue. All right, great. Great. So because of this vanishing gradient problem, neural networks were abandoned for a long time. But in 2010, Xavier and Joshua published a paper titled "Understanding the Difficulty of Training Deep Feed-Forward Neural Networks." And the authors of this paper suggested that the root cause of vanishing gradient problem is the nature of sigmoid activation function derivative. Okay, so basically they suggested that it was because of sigmoid, the way we just observed, that sigmoid is causing the values to become between 0 and 1. So they suggested that we could use something else. They could, okay, and so what is the solution for the vanishing gradient problem? The answer is multifold, and this is a research area. This is the research area, and last year itself there was a major breakthrough in this domain. You will see that as we go ahead. So it's an emerging area, and every day as we speak, a lot of changes are happening in this area. Okay, we are figuring out good strategies to initialize weights as well as better activation function. Okay, so in 2015, Kaming he, I don't know how to pronounce, Kaming he suggested strategy for initializing the weights. Okay, and uh, initializing the weights in such a way that the vanishing gradient problem could be avoided. It is called he initialization with the below parameters of various activation functions. Okay, so this might look a little daunting. So the way we initialize weights, instead of initializing using the normal min-max distribution, here we initialize the weights. You just instead of just doing random values, we initialize using the normal distribution. Or if you okay, so basically as per they suggested certain ways of distribution as well as activation function. If in our neural network we are using logistic function, then if we are using the normal distribution for initializing the weights, then the deviation of the values should be this much. Okay, so when we are generating random numbers, then those random numbers should have this kind of deviation, standard deviation. Okay, that's what the paper suggested. These are empirical numbers. These are, you can think of them like a constants, right? So based on number of inputs and number of outputs, you sum up these two and find the standard deviation by this kind of formula. And while generating the weights, the initial value of weights, we initialize such that their variation, the standard deviation should not go beyond this. Okay, and of course the mean is considered as 0. Around the mean, we should have this much of deviation only while initializing the values. Instead of having any kind of random values, or instead of only enforcing that the values must be between 0 and 1, they suggested that the initial weight should be kind of this. In case you are using uniform distribution, then use the range from minus r to plus r, where r is this. If you are using a 10h function instead of an activation function, we need to use this range, the value of range, negative of this, and positive this. So between minus r and r, where r is square root of 6 by total inputs plus outputs multiplied by 4. All right. So, right, if you want to find out like what does it mean to us, let's say if you want to use activation function in case of let's say MNIST, right? So in case of MNIST, if let's say we want to find out the and we want to use normal distribution instead of uniform distribution. Okay, so what we will do is we would do is let's say we are using logistic function, sigmoid function, then deviation will be square root of 2 by how much? Anybody? In case of MNIST, in case of MNIST, yes. How much will that be? It'll be 2 by number of inputs plus number of outputs. Yeah. 784. Good. Plus number of outputs. Right. So this suggests that this should be the value of deviation. Okay, the value of deviation should be this much. And while generating the value, the sigma should be generated in this fashion. All right. So basically this is the deviation. And what is deviation? We subtract the every value by mean and sum up their individuals deviation from the mean, and then we average it out. So right. Okay. In case of TensorFlow, we don't have to do that. Instead, we can just create one more layer called scaling initializer, variance scaling initializer, and we feed this here to kernel initializer. We basically create not layer, we're just initializing these weights here, and we are passing that initializer. We are instantiating the initializer, and we are passing that initializer as kernel initializer. Okay, that's what we are doing. We are using a function called dense. This dense function basically gives us a way to create a layer, and also lets us pass the object of the initializer, which will be called by at the time of initializing various weights. Okay, so we don't have to write the maths around initialization. We can just use the variance scaling initializer. It uses the hey initializer by default, the he initializer by default. All right, so this way we can easily initialize. Now here also notice that we are using a function called ReLU. Okay, so what is ReLU again? As compared to other activation functions, it was found out that ReLU performs better than every other function. Okay, ReLU performs uh, better than sigmoid, not every other, better than sigmoid. We'll talk about the problems with ReLU as we go ahead. So it turns out that ReLU function is uh, works pretty well. One, it does not become saturated for positive values, meaning it does not return a constant value, just like sigmoid. So, so basically, this is what is ReLU. ReLU returns 0 in case, uh, okay, in case Z is lesser than 0 or 0, or otherwise it returns the actual value. So for all positive values of Z, it will return the value as such. If the value it is value is called with negative number, it will return 0. So for all the negative values, it will return 0. For the positive values, it will return the value as such. Okay. So basically, this is a very straightforward function. It is extremely fast to compute because it's just probably a single line of code, and it has just a small single condition, nothing much. So it's really fast to compute. And it was found out that the ReLU function actually works pretty well. So the second thing, it is basically the not differentiable. That's a downside of ReLU. At value x equals 0, it is not differentiable. Okay, so that's a problem with the activation function ReLU. And now, since its value could be anything, its value would be kind of constant. For positive input values, the derivative of ReLU is always 1 because whatever is the input, it returns the output as such. So the rate of change is always fixed. Okay, the derivative is always fixed, constant, right? Therefore, it never vanishes. So since if you multiply something by 1, it will remain the same value instead of decreasing or increasing. So ReLU makes sure that ReLU, if you are using ReLU as activation function, the gradients will not vanish. Okay, and so now we'll continue from here after the break. Let's take a break for 10 minutes. Before the break, we talked about the ReLU function. Now, question to all of you is, do you see any problem with the derivative of ReLU activation function? Yes? Do you see any problem with the derivative of ReLU activation function? Right? Yes, there are only two values, 0 and 1. So will that create a problem in case of backpropagation? Yes. Great. So if the derivative is, if the value z is less than 0, the less than 0, then the ReLU function will return 0, and hence the derivative is always going to be 0. right? That's exactly the problem. So ReLU suffers from a problem called dying ReLU. For negative input value, it's always zero, and for negative inputs, the derivative is always zero. So because of dying ReLUs, during training, some neurons effectively die. The whole derivative, whole rate of change of error for the entire set of neurons could die. They stop outputting another the gradients would die, and hence the weights will not change, and this completely blocks the back propagation. So how do we stop the dying ReLU problem? It's called leaky ReLU. So instead of returning instead of returning zero, it starts returning a tiny small amount of value. Okay, say for example, when the input value is zero, it gives zero. But if input value is smaller, it gives tiny value instead of actual value. While on the positive side, on the positive side, here when the value is positive, the value return is exactly same as what is the input. Say for example 4, it gives you 4. So on the positive side it remains exactly same, but on the negative side, instead of returning actual negative value, it returns, or returning 0, it returns tiny negative value, where alpha is a hyperparameter. We would basically use this as a hyperparameter, and we call it like the leak. This function basically defines how much the value is leaking. So it avoids the overall values to become 0. Okay, this is small gradient ensures that the value never dies, and in the recent research it has been shown that setting of zero point 0.2, which is a big leak, um, results in a good performance. Okay, so this is how it looks like. Here we have defined our own leaky function, a leaky ReLU, where whatever is z and alpha, it returns the maximum of these two values, alpha multiplied by z and 0 and z. And then we plot this, and okay, let me just show you here. This is how it looks like. We've tried to plot it. So I hope this function is extremely clear to you, that it's a max of alpha multiplied by this or z. Okay. The other way, the same thing, we could also write it like this in a bigger form. It's, let me just show you what it means. Okay, make it a little more simple to understand. If z is greater than 0, return z, else return z into alpha. This is what it means. Okay, so these two functions, if you take a look at them closely, these two functions are equivalent. All right, if the value of z is positive, this will be bigger. If z is negative, this will be bigger because alpha is a positive fraction. Okay, so this is called the leaky ReLU function. Now it's pretty easy to use leaky ReLU. You can just define your own function here like this, and activation equals leaky underscore ReLU we can pass here. All right, so let me just see if we have used here. Okay, now if we, let's say we are defining our leaky ReLU and we are saying hidden layer equals this, and we are passing this particular function as activation. All right, we can train our neural network using this leaky ReLU. Again, in this we are creating the graph. Here let's try to create the graph. We are initializing the layer various constants, number of inputs, number of outputs. In case of this, we are doing for MNIST. Okay, and then we are defining x and y, the placeholders for the training data. Then we are defining the layer, like 3 layers. We are defining hidden layer 1, hidden layer 2, and the last one, logistic layer, whereby we are using the softmax by default. Okay, so uh, here we'll be using not softmax, we'll be using the sigmoid by default. And here then we are, oh, we have already defined it. I think yes. Okay, reset the graph. Okay, all right. So with this scope, we are defining the loss function here. Loss function basically depends upon our output of logistics, the last one. And we define the cross entropy here. Remember the cross entropy part. So we basically, loss is a function of cross entropy. Cross entropy is a function of the last layer. Okay. So cross entropy basically does both softmax and cross entropy. All right. So then we are starting to define the optimizer. Then we are defining the training operation and so on. So, okay. And then finally, we load the data here, and then we load the data and we execute it. Okay. So you can see that with leaky, it is running, and batch size is 50 and number of epochs are 40. Number of epochs are 40. Okay. So it's going to take some time to execute. You can see that the accuracy here in case of batch, you can see here it's reaching 1. That means it has started to do the overfitting. Okay, not yet. I think I'll show you. So slight amount of overfitting is happening right now. It'll take a while to finish it. All right. So this is the accuracy that we got, 97.8%. All right. So you can see that with ReLU, we're getting good enough results. Okay. All right. In 2015, in 2015, Jork, Arne, and Clavert proposed, and the ETL and the company proposed a new activation function called ELU, exponential linear unit. It outperformed all the ReLU variants in their experiments. Training time was reduced and neural network performed better on test set. So it basically outperformed all the ReLU variant in their experiments. And training time was reduced and neural network performed better on the test set. Okay. So what is ELU? So ELU is essentially on the leaky side, you see, on this side, it is giving e to the power that value -1 multiplied with alpha. This is the ELU, as in when the values of Z is lesser than 0, then value of Z lesser than 0, or sorry, let's just, yeah. When the values of Z lesser than 0, then you use this formula. Okay. So
Basically, you can think of it some way like slightly like some way like sigmoid. We are using the exponential here on this side and giving the output. So, so basically the LU function also worked pretty well. Okay. So this is the difference between the ReLU and LU function. Okay. Now the drawbacks of the drawbacks over ReLU function are that because of use of exponential, there is a computation involved. This part instead of just returning zero, here it's returning some value which requires some amount of computation. Okay. Then this slowness is compensated by faster convergence rate. Okay. It was observed that when we use ELU function, we generally the results are converging better, and the ELU networks are slower than ReLU networks, and right. So in computation, this is basically though it converges faster, but still the individual slowness is there. Now let's try to take a look at the outcome of ELU. Okay, so this is how it looks like, and we can just use our the TensorFlow provides a function called ELU inside NN, inside the package NN, and you can just use that one. All right, you don't have to define. So just on the while defining a dance layer, we can just define this. All right. So in 2017, Gunther, Thomas, and Andreas, they proposed something called SELU. It outperformed every other activation function very significantly for deep neural network, even for 100-layer deep neural network. So this is how it looks like. So we are defining SELU like this. So whatever, basically here, all it does is it scales the value of ELU. Basically, it's nothing but scaled exponential linear unit. This is what it is, right? And this is how it looks like. So basically, we multiply it with a scale to the ELU value, and that's what it does. And this is how it looks like. So important part is this function here. So the default value scale is around 1.05 and 1.63. Okay, that's what it is. Now moving ahead. Now, with this activation function, even a 100-layer deep neural network preserves roughly a mean of 0 and standard deviation 1 across all layers, avoiding the exploding or vanishing gradient problem. Okay, so if you check the mean and standard deviation in the deep layers, you will see that right. So let me just show you. Okay, so this is how it looks like. What happened here? Okay, let me just execute from here again. Now, so here you can see that we have defined the SELU function, and SELU function basically looks like this. And you can see that here what we are doing is we are kind of creating these layers. We are basically doing the iteration where next value is a function of previous value. Okay, that's what we are doing. So even in that case, when we call SELU again and again on the same value, the the you can see that the standard deviation and the mean is kind of fixed. Okay, it's not vanishing. It's not vanishing. And if we train the neural network with the SELU function, the we'll get better results. So a question from James is, why is SELU significantly different from ELU? ELU is basically, SELU is essentially an improvement over ELU. it basically just multiplies a particular number, just particular number to the value. It just scales it. Okay. And yeah, so basically it gives out a particular value for alpha and then calls the LU just like earlier and then scale it up. Okay. So this LU is basically slight improvement, slight change over the values, and the it works better because it is increasing the value here like this. Instead of taking the value 2 minus 1, it's taking beyond minus 2 here. Okay, so we get two more hyperparameters to tune, like scale and alpha, which we can experiment with. Okay, so the reason why is SALU significantly different to ELU? It is not significantly different, just that it is slightly different. And since the value is little slow, bigger than 1 and minus 1 and smaller than minus 2, the values are not vanishing. That's the important part over a period of time. Right? Most of the research that you're seeing, these functions have come from experimentation, and most of the basis for this work is empirical. Okay. A question from James is that why is it important for the mean to be 0 and standard deviation to be 1? So that means that it won't explode. If the mean, basically the values of various things would remain there, would not explode. That's the purpose of staying within the one standard deviation. One standard deviation is a huge deviation because like within like 3 standard deviation, you actually cover a huge range. So when one standard deviation is actually good enough in the natural things, around 70% of the data is within one standard deviation in the normal life. Therefore, one standard deviation is a good one, and it will make sure that the values don't explode or don't go dramatically high. Similarly, the mean to be 0 means it should remain both sides, negative and positive. That's the core idea about keeping the things within one standard deviation. Okay. So when we say something is within one standard deviation, we call that person as normal, right? And if things go beyond, say, 2 standard deviation or 3 standard deviation, things become outlier. All right. Was I able to explain that why do we need to? uh, All right. All right. Good. So all right. So basically, the core idea behind SALU, actually, most of these, whether ReLU, ELU, and SALU, they all of these functions have come by experimentation mostly. And okay, so you can see. All right. So in these cases, the values kind of remain within one standard deviation. You can see. All right. So with the say SALU, we could actually run it and see the accuracy. In above, how much did we get the accuracy? In here, the validation accuracy was 97.8. All right, let's see how much it is. Okay, it's executing. So we have, So this is the accuracy after 25th iteration. Okay, so this was the accuracy earlier. We'll just keep this. Right. Okay, so all right. Okay, so here in this case, the accuracy is not that great because the okay accuracy is not that as in accuracy is almost like same as what we did earlier, and this is basically okay. Now a question is right. So actually here in our case, it's not performing that great actually. Okay. A question from Pratik is, can you explain the use of epochs? Definitely. So what we are doing is we are running this whole iteration again and again. So this one from here, right? Here we are breaking our data into batches. Okay. For each batch, we are training our neural network. We are running the session here. Okay. We are running the session and we are training our we are basically this is where the training is happening for each batch. We are passing that batch after scaling and so on, and the training is happening at this point. Okay, so here we have broken down entire input data into batches, and we are training it. This particular part is only for printing. Now here, what we are saying is run this training around 40 times. We are printing this around 40 times. Okay, that's what is happening here. Okay, so we are just basically doing the same thing over and over 40 times. So we are feeding these total images in the batches, and that too in 40 times. Okay, so our this training is happening 40 times on the same data. All right. Now, right. Next question is from Bintao. How does scale equals np dot square root 1 by 10? Okay, where is that part? Which part are you referring to? So here, I think I got it. So this is what you mean probably here. Okay, yeah, here, right? All right. So see, yeah. So here what we are doing is we are initializing the weights with the normal distribution, okay, normal distribution, where the range is going from 100, where the size is 100 by 100, and the scale is this much. Okay, that's what the weight initialization is about. Okay, so that's what is the weight initialization. So here we are generating the random numbers using a normal distribution with this dimension 100 by 100, and we are passing the scale here. Okay, so that I think we here when we are passing the scale is it would be the standard deviation. Most likely we are passing 1 by 0.1 as the standard deviation. Okay, we're passing this as standard deviation. So yeah, I mean that he initialization probably. Okay, and all right, is that what you mean? Okay, good. So here we are, and so we can see that we have trained our model using Celu. The overall performance does not seem to improve much in this particular case. Maybe for other cases, it could be improving the performance. All right. So this was what we call as Celu. All right. So should we move forward? A general question is that there are so many activation functions. Which one should we use? In very simple words, in very simple way, SELU is considered generally better than ELU. ELU is better than leaky ReLU, which is better than ReLU, which is better than 10H and logistic. Okay. 10H, 10 inverse H, actually 10AH, it is the that hyperbolic tangent function. This one and logistic both suffer from vanishing gradients, while ReLU doesn't. ReLU has a problem with multiplying with 0, where that is overcome by leaky. And here further that is enhanced by putting it exponential. And then we put a scaled exponential. So this one is far better. Okay. A question from Binta is scale equals deviation or initial value here? Scale is deviation here. Okay. So while generating the random number, let me go back here. Okay. While generating the random numbers, yeah. While generating these random numbers using the normal distribution within of this size, this dimension 100 by 100, we are passing the standard deviation. Okay, so that these numbers, when they are generated randomly, they should not be just any random, but within a certain deviation. All right. So this is basically I think this slide sums up all the discussion we have had so far. Okay, in this session. So out of all of these, SELU, the SELU, seems to perform better than other activation functions. Okay, so if runtime performance is important, then if you're in your situation, if you want the training to happen really quickly, then then prefer the leaky ReLUs over the LU or SELU. Okay. Also, instead of tweaking the hyperparameter alpha, we may use the default suggested value. Okay. So if we have spare time and computing power, we could basically do the cross-validation and figure out which activation function along with which hyperparameter is good for you. Okay. So the mileage of tweaking the activation function might vary from problem to problem, and In general, SELU is better, but it is a little slower. Therefore, a better idea is if you have extra CPU available and time available, then you can let let it compare the results of various strategies. Right? Now, the other very important technique called batch normalization was brought into picture to avoid the vanishing gradients and other problems. Okay, so using he initialization and proper activation functions like ELU or other variants of ReLU, vanishing exploding gradient problem significantly reduces. But there is no guarantee that this problem will not come back during training. In 2015, Sergey Loev and Christine said Sergey proposed a technique called batch normalization. Okay, in 2015, this technique called batch normalization introduced to address the vanishing or exploding gradient problems. So you can see that most of this research is actually fairly new. The CELU is, I think, 2016, and most of the research is actually kind of happening, and a lot of experimentation is going on in this area. And from time to time, these techniques are being updated. All right. So that does not mean that whatever we are studying is useless. Instead, it is far more relevant because whatever changes that happen, they happen on the foundation what we've learned so far. A lot of changes are happening only on that foundation. So batch normalization was to address the vanishing or exploding gradient problems. And batch normalization helps in vanishing gradient problem, and it also helps the neural network to learn faster. So let us understand the batch normalization. As discussed earlier in machine learning projects, gradient descent does not work well. Okay, if the input features are on different scales, correct? So we generally scale our input before feeding it to the neural net. Like say if we have number of miles individual has driven in last 5 years, the data can have a large varying scale. At someone who might have driven 100,000 miles while other person might have driven 100 miles, and so here the range is from 100 to 100,000. So the data could vary enormously between one instance to another, or within the same instance the value of various features could be really different. So the batch normalization is a very important technique, and the way we do is we basically do the feature scaling, right? So one of the techniques that we learned in the beginning chapters that before feeding data to any machine learning algorithm, we do feature scaling. And feature scaling could be done by using min-max scaling or using standardization. Standardization, features are rescaled so that output have the properties of standard normal distribution. Okay, when we plot the output's frequency, it should look like a bell-shaped curve. In this bell-shaped curve, please remember that on the y-axis, it is the number of instance on this particular value. Okay, this particular value, there are a number of instances. So on the y-axis, it's always the population as a number of instances on a particular value. So in standardization, features are scaled so that output will have this following property of standard normal distribution with zero mean and unit variance. Okay, earlier we talked about initialization where we were initializing the values with normal distribution. Here we are normalizing the input. We're normalizing the input such that the mean of the values become zero, and the standard deviation remains. So we are scaling or standardizing using a particular mean and a particular deviation. All right. So this is how it goes. So the general method of calculation is that calculate distribution mean, meaning we find the mean first. Then we find the standard deviation of each function, each feature, not function, each feature. Subtract the mean from each feature. That's how we compute the standard deviation. And then divide the so subtract the mean from each feature and then divide the result from previous step of each feature by standard deviation. This is what it means. So first of all, compute the standard deviation. Then we compute the delta of each value from the mean. And then we divide each of the values, by the standard deviation. Okay, so the standard value that comes out, what does it mean here? Here it means that how many times the value is away from the mean, how many standard deviations. Okay, so if this value is really huge, like 4, that means your data is an outlier. If this value is say 1, this data is normal. Okay, so how many standard deviation away is each value from the mean? From the mean. So that's what this x dash means, and that's how we are standard. So instead of actual value, we are keeping how many standard deviation is each value away from the mean. That's what we're keeping. So as a pre-processing step, we apply standardization to input data set so that all the features will have the same scale and so on, right? So here these are anyway the input on the input layer, we have normalized input features. And okay, so if we normalize hidden layer also in the deep neural network, then it'll speed up the learning. So usually while we start a machine learning project, input we standardize, right? We standardize input, and that gives you the results really well. So in the batch normalization, what we do is, while doing the computation here, at every hidden layer, we also normalize that. All right, so we normalize the hidden layer as well. Now let's understand how do we do batch normalization deep learning. So this is what we do. So here what we do is we basically, let's say from these x1, x2, x3, by multiplying the weights, we'll get these sigmas. These sigmas are computed by x1 into w1, x2 into w2, plus x3 into w2 by summing up these values. Similarly, this one. Now, after that, we do the batch normalization here. All right. After this, we do the batch normalization. And after batch normalization, we hand over the value to the activation function, and then whatever is the output goes to the next layer. So here, first, the input is being combined into sigma, then sigma is being normalized, then normalized values are fed to the activation function, and this whole thing, these three operations are happening at every hidden layer. Okay, so this is where the batch normalization fits in. Okay, this is where batch normalization fits in. So, and again, let's take a look at this one. The hidden layer 2, here the calculation goes like this, where we had these input instance values. Then the instance again is a batch. There are multiple instances being fed to it. Okay, then the values are summed up here. After summing up the values by multiplying the weights, we compute the normalize. We do the normalization standard, then the using the standard deviation of batch normalization. This is where we do the normalization, and afterwards we feed it to the activation function. Then next step, then we sum up the values here by multiplying the weights, and then we do the batch normalization again, and then we feed it to the activation function, and whatever is the result is sent to the output. So this is what goes on in case of normalization. So again, let me readdress how does the normalization algorithm works. So for T in the number of mini batches, so let's say we have 60,000 images, we will create a batch of say 50 images, and for each 50 image, we do the normalization. That's called a batch. So compute the forward propagation for mini batch. In each hidden layer, normalize the inputs and use back propagation to update the parameters. Okay, so let's say we have a simple network, and here normalizing input features help in calculating W and V. This is how it look like. So once we have computed this value, so so imagine that we have a very simple network where we got this batch. Now what we are going to do is, first of all, for this batch, we are going to normalize, we are going to calculate the mean. Then we are going to compute the standard deviation. How do we compute the standard deviation? We subtract the mean from each instance, square it, and then average it by dividing total number of instances. And then basically that's is the standard deviation. Then we normalize it. How? We normalize by subtracting each value by mu and dividing that. Also notice that while we will be computing x minus mu, we will be computing it twice. And therefore, this computation by TensorFlow will be only done once and used twice. Okay, so that's a tiny optimization you can obviously see. And because here also we computed the same value, here also we are computing the same value. So here what we are doing is we are dividing by sigma. Now here's a little twist. Instead of dividing by standard deviation just like this, we are adding that to adding a tiny value to it, adding a very tiny value to it, so that tiny positive value, so that this never gets infinite. If this sigma is 0, if the standard deviation 0, the chance of this becoming 0 is there. And therefore we have added epsilon to avoid the divide by 0 error. Okay, so this is what we are doing. So we are first computing the mean, then mean of the mini batch. Remember, in case of every neural network, when we are training them, instead of sending the whole batch in a single shot, we send a mini batch to the neural network for training. So for that mini batch, we first compute the mean, then compute the standard deviation, then we compute the normalized output by subtracting each value by the mean and dividing by the standard deviation. A question from Pratik is, but X can get very high because of small EPS. X can, yes, that's correct. So the X can get very high because of that, but that's really rare, right? Because if something has a very tiny standard deviation, the chance of this value is going to be really tiny. So this value is going to be really tiny, and this is also tiny. So that is going to be a normal number, right? So when will the standard deviation be small, right? Standard deviation of all the numbers will be 0 when all of the numbers are at the mean, correct? Only then. If all of the numbers are on the mean, therefore this will be 0 anyway, correct? So even if one number even if let's say except for one number, all numbers are on the mean, then also sigma will be positive. Okay, so yes. All right, next is that now the last step is the one that is an extra. So in the batch normalization, what we do is whatever we have computed previously, we multiply it with gamma and add it with beta. These gamma and beta are not hyperparameters. They are the parameters which are learned during training, which are learned during training. All right. So in the batch normalization, we first normalize the input, then we multiply it with gamma and add it with beta. And that these gamma and beta are learned just like weights and biases. Okay, this is called the batch normalization. In general, we have four parameters are trained for each batch normalization layer. One is sigma, mu, gamma, and beta. All right. Now, here we were able to compute this the mean and everything for mini batch, right? While we were training our neural network, we passed data in the set of in smaller sets like in mini batches, correct? But in case of the while we are testing, while we are running it over real data, we may not have a mini batch, right? We will have one record or two records to test against. Then where will we bring where will we bring the mean from? Because mean for a single record, if we just keep it the same as the actual one, it doesn't make sense. So we actually use these values even at the test time. Okay, so at the test time, how do we test the deep neural network trained and batch normalization, as there may not be any mini batch to compute the mean and standard deviation, right? So in that case, what we do is the strategy for training and testing changes a bit. For training, we have the mini batches. For testing, we don't. So what we do is we utilize the values of mean and standard deviation from the previous batches while doing the testing. Okay, by computing the moving average of the whole training set's mean and standard deviation during the training. So this is what we basically utilize the mean and standard deviation from the time of the training. All right, so now let's take a look at it. All right, so here is the batch normalization. So let me just walk you through this code. Okay, so here we are resetting the graph. We are initially importing the TensorFlow. Then we are defining the various constants like number of inputs. First hidden layer is going to be 300 neurons. Second one is going to be 100 neurons, and the output is going to be 10. Okay, then we are defining the placeholder X, and then here we are defining the placeholder for training. Okay, here this is a scalar value, true or false. Okay, we will pass this from the outside. Whether we are training or testing, we want to control that. We want to have one variable controlling whether we are doing the training or testing. That's why we have created one variable there. Okay, so either we could define this Python boolean or a TensorFlow boolean. Okay, and okay, since for me the okay, I just zoomed in a bit just for this line. Um, okay, okay. Let me zoom out a bit. Yeah. So here we are initializing capital X. After that, we are defining training. Here, instead of defining Python Boolean, we are defining TensorFlow Boolean. It's essentially a flag that marks whether we are trying to do the testing or training. Okay. Then we are defining, let's say, one layer of hidden neural network. Then after this hidden layer, we are putting one layer, kind of a layer called batch normalization. We are inserting one layer just after dense. This looks like a layer. Actually, we just are normalizing the values. And here we are saying hidden, we're passing the hidden value, the previous one. And then we are specifying whether it's a training or testing. Okay. Once that's done, we're basically passing one more argument called momentum. Okay. We will talk about momentum later. All right. So we are passing one more argument called momentum to the batch normalization. Now, we'll talk about the momentum again. So essentially, the batch normalization is normalizing the inputs of the previous layer and giving it to the next layer. Okay. Then we are again doing the same thing with the second hidden layer. Okay. And once that's done, okay. So we basically are normalizing after every hidden layer. Okay. Now the same, you can see. So we are calling the batch normalization thrice after every layer. Okay. Now what we are doing is we are now going to execute this. Okay. We are going to execute this. All right. Here the X placeholder, this is all okay. We are defining these values for, okay, why was this needed? We have already defined it, right? Okay, right. So yeah, one more thing is basically in the previous example, we repeatedly passing these parameters again and again, right? Here training equals training, momentum equals to this, and so on. So this was being passed again and again. These here, here, here. In Python, in Python, we can avoid doing this by using a function called partial. Okay, we could just define a partial function and then call that with only one argument. So this one we will have defined it earlier. Okay, and then don't have to pass this again and again. So here we are defining a partial function. Okay, here we are defining a partial function. We are saying that the same thing. Here we are saying that partial takes this value as the first argument, and this value, basically we are saying that on this function, feed in these values when somebody calls this. Okay, you can actually, this is basically a functionality from Python. Python lets you do that. Python lets you create quickly a wrapper over an existing Python function with, for certain fields, we can specify the default values. For certain of the arguments, we can define the default values, and then we can reuse this. So every time we are going to call my batch layer with some values, these arguments are going to be automatically appended. Right? For example, here when we are calling this function at this point, you see, we are just passing one argument. Remaining arguments are coming from here. So this is going to call this function with these two extra arguments. These two extra arguments. No, it doesn't refer to the partial derivative. Okay, partial is a general function from Python. You can just try this. So let's say we had to um, do we could say um my square function, okay, equals to pow, okay, and we could say partial pow and 2, right? You could do that, right? Do we have a pow function? I don't remember. Okay, so do we have pow function or do we need, yeah. So pow 4 equals to 2. All right, so something like this. So we basically can define my, I'm not sure if it'll work. I've hardly used power function. Now it's doing something else. Okay, so it's calling this with 2. Oh, it's doing 2 to the power 3. Okay, okay, it's doing 2 to the power 3. All right, so basically, okay, I could give a better example. Mm, okay, there could be many such functions whereby if you want to do something, um, okay, this is actually the other way, like we call it um, 2 exponent, right? So whatever value we are passing, if we say 2 to the power 2, it'll return 4. It'll, 10 means 2 to the power 1024. Right? So that way, okay. So you can see that when we are calling these functions, these two, this function is being called with this argument as the second one. Okay. I hope you got the picture. Question is it equivalent to map in Python? Kind of it is map, but not much. It's essentially it is essentially creating a function which is a wrapper, right? If you have a particular function and every time you are calling, you're passing the same arguments again and again. So it's better to just define a wrapper over that function and then call that wrapper. That's what is partial. Partial is creating a wrapper over the function. Here, let's say what we are saying is partial, this function, and these are the two arguments. Okay, so it has created this wrapper. What this wrapper does is every time you call this wrapper, it's going to call this along with along with these parameters, along with the actual parameters. So here when we call batch norm hidden, what's going to call is it's going to call this with n hidden as our first argument, then remaining as the other arguments. Okay. Instead of you typing it again and again like this, you are just now going to call my batch normalization layer with only the hidden layer because that's the only part that is varying. Rest of it is same. Okay. So this is basically the example of partial. Now we have dense, we are defining this now batch normalization layer, then we are doing ELU, and then again we are defining another dense layer. Again, we are defining a batch normalization layer, and then we are defining ELU and so on. All right, now let's try to train it. Try to train it with the batch normalization. What happened to this? Did we clear the graph? Yeah, let me try again. Okay, so it has started the work. Now, once we have trained it, Okay, so you can see that here here we are having something called extra ops. This is something important to understand. So essentially, we are saying the update ops. Update ops, basically the extra ops are the mean and the standard deviation. That's what we want to compute along with it. So we can utilize those parts, those parts in the computation. So while doing the computation, we are saying execute the update ops as well. On every computation, we are asking it to execute the update ops also. Okay, that's the difference between the previous approach in this one. So we are asking TensorFlow to run the extra updates. Okay, though this is not a great accuracy for MNIST. Okay, but if we just train it longer, we might get a better accuracy, and with more layers, it would definitely improve. Okay, so right. So while doing this, it's doing a couple of more works under the hood. It is computing your moving averages so that we can train on the moving averages. And so moving averages are basically not trainable variables. And therefore, the list of trainable variables is bigger than the global variables. Okay. So sorry, you can see a list of trainable variables is smaller than the global variables, because global variables we can see their moving average, moving mean, and so on. Every time one iteration is happening, it is keeping track of the moving average and moving variances. Okay, and why? Because we have in mentioned that we need to do the update ops. Okay. So these are the extra variables it's computing other than the usual graph. That's why we had asked it to execute. All right. Now, this is essentially, right. Now, when we are testing, that is one part that we left. Okay. So, okay. Here we are saying accuracy.eval in order to test. And what is accuracy? Accuracy is defined above. Okay. Accuracy is defined above, just like usual way. All right. Yeah. One more thing you must notice is something that we have missed here. While doing the training here, right? We are calling this with the training equals to true. We're calling the training with training equals to true. Okay, right? This variable called training is true while doing the training. So, and while doing the testing, we basically will be passing the training as false. Why we have not passed it? Because training is by default false. Okay. All right. All right. Let me try to explain it once more. I'll just walk you over this. So as we discussed that while we are using the batch normalization, the training and testing differs a bit. How? At the time of training, we have batches of data. We are passing batches of data so that there could be, so we are passing the batches of data, and then we are doing the batch normalization, right, at the time of training. But at the time of testing, we have single instance. If we try to do normalization of it, it wouldn't make much sense. So we want to reuse the values of mean and standard deviation from mean and standard deviation from the previous batches which happened during at the time of training. Okay, we could actually run the same thing again and find out what was the mean and standard deviation, but it wouldn't make sense. Therefore, at the time of training itself, we kept a record of the values. We kept a record of what were the values of mean and standard deviation, and then you use those values at the time of testing. And how? By just informing TensorFlow that we don't want to pass this variable called training. We want to we want to mark that training is false, and that signals TensorFlow that, hey, we want to reutilize the mean in the which is used previously. So, all right. So that's what is happening here. And let me just show you. So here we are defining a variable called training. Okay. And doing the partial normalization, here we are calling this batch normalization with a flag called training. This this method this method called batch normalization has a function, has an argument called training. Okay, so we are passing that argument, and while doing the normalization, if we pass this as false, it will basically utilize the previously computed mean and standard deviation instead of trying to compute on the testing data. Okay, so that's what it does. All right. So that basically batch normalization cannot happen if there is no batch, right? Therefore, we need to retain the values of mean and standard deviation as computed during the training when we had batches, and then reutilize it on the reutilize those mean and standard deviation on the testing data. All right. That's why we have extra variables. That's why we have we have here we are running extra update operations and so on. All right. Did I make sense to you? That's why we have more variables than the trainable variables, because mean and standard deviation or moving variance or moving mean is not counted as trainable variables. All right. All right. A question from Mintao is that tf.get collection this. Okay. So you can ask TensorFlow to give you the ops, give you the graph nodes by using tf.get collection. Okay. You can take a look at this. So this let me explain again a bit. There's just a couple of more things extra here. So this, you see, when we are creating the graph above, while we were using this function here, when we are using this function here, which is nothing but calling the batch normalization function. This would be creating more update nodes. Okay, this would be creating more update nodes. Let me just show you in the documentation what it means. Okay, so here it's basically based on their paper. Okay, here when training, the moving mean and moving errors needs to be computed. By default, the update ops are placed in this particular key. Okay, so essentially these since inside this function it is computing these things, right? So it's putting is putting these graph nodes under this. Okay, under this, you can take a look. Okay, you could take a look at this. All right, so here you can take a look. These are called update ops. Under update ops, it's putting those extra operators so that you can call them at any time. You can call them at any time. Can I call them at any time? Let me check. So if I say this is my new session I'm creating, and I'm saying, okay, I'm saying session dot run, and what were those variables? Okay, like this. Okay, all right. I think okay. So what is it does is, okay. So basically we need to do it in the same graph here. We need to do it in the same graph where we are computing the other values. So we will have to call this here just after we have got the batch. So after we have done the training up, only then we can call that. Okay, so that's why we run in the same graph. Okay, all right. So all right, basically I think we got this. Yeah. All right. So essentially this particular extra ops, why are we doing that? So that moving average and other things could be computed along with this and could be retained and used, and which we can utilize at the time of testing. Okay. When we are calling the accuracy.eval in the same session, the things that we were computed here would be utilized in the computation of accuracy. Okay. All right. Yeah. Was able to make it clear, Vinta? So these are the internal, when we are calling the function of batch normalization, it places those extra methods under this node in the graph. That's why we are extracting that particular node and executing it while running the usual training operations. And then once it is done, the values of mean and other things would be computed, and using that we could just using that we could just test the testing data and even the individual instance. All right, so that was the objective of batch. That was what the batch initialization was all about. So batch initialization is used quite often while training the deep neural network. Batch initialization behaves as if there is one extra layer in your deep network. Okay, this one extra layer, all it does is it takes data, it takes the input data, normalize it, and gives it to the next layer. That's all it does. All right. So we will continue from gradient clipping tomorrow. All right. We'll continue from gradient clipping tomorrow. All right. Thank you, everyone. Thank you for great patience. tomorrow we are going to start from gradient clipping, and there are few more things we will be also learning about how to reuse an existing trained network. We call that transfer learning. So tomorrow with clipping and transfer learning, we'll be continuing. Next week we'll be starting with CNN and the RNN. All right. Thank you, everyone. Have a good day. All right. Bye bye. Thank you, Balaji. Thank you, Bintao. Thank you, Prateek. Have a good day.